Okay. It is my very great pleasure to welcome you all to the final plenary talk of the Maple Conference 2021. It is also my very great pleasure to introduce to you Dr. Evelyn Hubert. Evelyn has been a plenary speaker at the Foundations of Computational Mathematics Conference, arguably the most serious of all the computer algebra conferences, and she is on the editorial board for the Foundations of Computational Mathematics, and has been a well-known researcher in the computer algebra world, at least since her postdoc at the University of Waterloo. She has been a fellow at MSRI and most recently a fellow at the Isaac Newton Institute in Cambridge, where I last saw her. She's a Simons Fellow there. And this is evidence of Evelyn's impact in the computer algebra community. She's a senior researcher at INRIA Mediterranee, Sophia Antipolis, and this position doesn't really have an exact analog in the university system in North America, but it's more or less equivalent, I think, to a named research professorship. So she gets to deal with she has the time and the focus to deal with the really hard problems. And at the same time, some of the really hard problems turn out to be really, really useful for lots of people. And today she's going to be talking about a surprising application of algebra to dimensional analysis. And so with that, I turn the talk over to Evelyn. Please, go ahead.
Rob, very nice to see you. Yeah, we had a good time at the Newton Institute. It was so interesting too. So all right, so my talk has a very long title, and and I should first and foremost say that this is my talk is going to be mostly based on at least the theoretical content was developed with George Laban in an article that was published in 2013, so some time ago. But this is a topic I feel really needs to be to gain some momentum, and that's why I choose to speak about it today. So without too much ado, I will start, and my starting point will be two kind of examples that will try to first of all kind of convince you that scaling symmetry is super important and everywhere, and how to use it in parameter reduction in mostly the problem that alerted my attention was in models coming from biology, mathematical models from biology. So the first, if you've done a little bit of physics, so I'm not going to go on with this semi-physics type of speech. I'm going to be back to math completely, but just this is kind of trying to convince you that scaling symmetries are everywhere. And in physics, it translates into this idea that if you have a meaningful differential equations, well, all the terms, that is, if your equation is a sum of different terms, all these terms, they should have the same dimensions. And by that, I mean that it should be expressible in the same units. So the dimensions are kind of a sort of a monomial in some kind of fundamental dimension, which are, for instance, the mass, the length, the time, temperature, etc. And so just as an example that you might all remember is the case of throwing a ball in the air, like this tennis woman. Well, I mean, if I'm trying to describe the height Z of this ball, I will have to write its equation, and it will come from, first of all, the law of motion that says that the acceleration multiplied by the mass is equal to the force to which it's submitted to. And this force is the gravitational force that we can write as proportional to the mass of the ball times the mass of the Earth, capital M. And then with the distance between the two centers of the ball and the Earth, I know it's disproportionate. So that would be big R for the radius of the Earth and Z for the height. So you end up with this equation here. And what should be completely apparent to you here is that these terms and this term, they are in the same dimension. And that is dimension is length to the cube, time to the square, time to the minus 2 squared. Sorry, time power minus 2. So there is a typo here, I apologize. So this is the point of this dimensional homogeneity, which is kind of a big physical principle that can be said as, you can't add apples and oranges. So now I want to say that, you don't need to know all this physics or these units and these dimensions. You could have recovered somehow the information by observing that if you scale your these variables Z and R, which are length, by a certain lambda, so it's like changing the unit in some sense, and then the time is going to be scaled by tau, and the mass by mu, and then G, the gravitational constants, has to be scaled by this monomial in lambda, tau, and mu. Then you will see that if you plug this transform in your equation, you obtain nearly the same equation up to a factor. But since this has to be equal to 0, it's basically the same equation. So this thing is known as a scaling symmetry, because we're kind of just rescaling each component by some monomial in some parameter, the parameters here being lambda, tau, and mu. So the point of this slide is that scaling symmetry is everywhere, and it really pays to take it into account. In particular, if you go along with this dimensional analysis theory, you can go up, maybe theory or practice, I should say, then you can deduce some very nice things like how to, from the Earth and experiment on the Earth, you can recover good equations that will work on the moon as well. So I'm not going to go to this this end, but let me switch to my main topic, which will be parameter reduction. And if you look into a book on modeling biology, mathematical modeling of biology, there is this predicament that the first step in analyzing a model is to reduce the number of parameters. So a typical example of mathematical modeling in biology would be the prey-predator model that kind of describes the dynamics of the rabbit and fox population. So the rabbits will be N, the fox will be N and P will be the rabbit, I think. I don't remember. And it's the population of rabbit and the population of fox. And the other comes into this model, a bunch of parameters, which are constant, that kind of describe the environment. So the availability of food, the area to cover, and hence the number of encounters, the ratio of encounters between rabbit and fox, etc. So here you have 6 parameters. And if you want to analyze this system, I mean, with 6 parameters, it's quite a lot of work, especially that if you have some combination of parameters, which will give you exactly the same values for the rabbits and the fox population. So if you look in some of the books, this parameter reduction is a bit of an art form. So by examining the system, you can figure out what are the new variables you want to introduce. So here the new variables that you introduce is a time that is a rescaling of the previous time, and it's rescaled by one of the parameter. And same thing for the population of, let's say, rabbit, that is rescaled by a parameter, and P is rescaled by a monomial in the parameters. And then we keep, the thing is that we keep only 3 parameters that are combination of the original parameters. And if we use these variables, you can actually see that the system can be rewritten in exactly those state variable, the populations, and the 3 parameters. So we see that the analysis of this system that depends on less parameter is going to be smaller. And so my point here is that we're going to make this process of finding the new variables and rewriting the system completely automatic. And by that, we will see that these strange variables, these new variables, will be obtained as the invariants of the scaling symmetry that is underlying this model. So let me say that this dimensional analysis of computing invariants of scaling symmetry is kind of already a known subject that you have probably encountered in your applied math studies. It's known as surrounding the Buckingham Pi Theorem. It might have some other denomination as well. And this Buckingham Pi Theorem allows you to say how to compute a number of a functionally independent set of invariants. And if I take the analogy of the first slide, that those are the dimensionless variables. And this computation is made simply with linear algebra. So that's really kind of cute and very easy to do. So what we will add to this original theorem today is that we will also determine, let me first say, we will first look not only at linear algebra, but linear algebra over the integers. So we will strengthen the type of invariants we will compute. They will not only be functionally independent, they will be generating, in the sense that any other invariant will be a polynomial in those invariants. We will also, with the same type of technique, be able to determine the scaling symmetry of the differential system. And actually doing these 2 things, we will obtain 2 side products at no cost. First of all, we will be able to obtain rewrite rules that will allow us to write the original system and in the reduced parameters, and new variables. And we will also say how to, if we have a solution of the reduced system, how we can obtain solution of the original system. And this will be given in terms of very explicit formula. So what I'm doing next is to kind of make explicit these 4 points on the example of the prey-predator model. So the scaling symmetry is given by 3 parameters, eta, mu, and nu, and it is a way of rescaling each of the element, each of the variable and the parameter, so that the system remains the same in the sense of what we saw in the first slide. So that our equations are homogeneous with respect to this transformation. From this scaling symmetry, from the description of this scaling symmetry, we will be able to compute its invariants. And its invariants are exactly these new variables that we introduced, not knowing where they were coming from. We will also be able to say how we rewrite how to obtain the reduced system from the original system. And this will be by just making the following substitution. So observe that the first substitution is just sending some of the parameter to 1, so erasing them from the equation. And the others are very simple substitution. And it will be often like that. And the second side product we will obtain for free is how to write the solution of the original system, n of t and p of t, in terms of the solution n of t and p of t of the reduced system. So n being the variable of the reduced system. So to go a bit ahead and get you familiar with how we will this will be done, and as I said, with linear algebra, you have to think that we're going to represent many things in terms of matrices. So for instance, this scaling symmetry, we saw that it was given by some monomials multiplying each of the parameters or variables. These monomials are going to be summed up. Their exponents are going to be summed up in a matrix. So for the variable s, we will have the rescaling is by eta to the power -1. And so this first column will be -1, 0, 0, etc. So each monomial here will be written as a column. I mean, its exponents are going to be written in the column of this matrix. So the scaling symmetry, the scaling is represented by this matrix. Another case where we're going to use matrices to represent the objects we are dealing with is, for instance, here. So my new variables, the generating invariants, are, as you can see, monomials in the former variable, in the original variable. So this we will write if we put all this new variable in a row vector, then it's going to be, we are going to write it as a certain row vector of the original variable, and the exponent of the monomials are going to be in this matrix here. So for instance, if we look at the t here, t is time, I mean, new t is r times t. And so you can see that in this column, the first column, we have one at the first element, at the first entry, and one at the last entry. That gives you that the t is equal to t times r. The second point, the last point I want to make in this introduction is, why do I claim that we're going to bring something by looking at things over the integers? Well, let's look at this model, which is also taken from the book by Murray in mathematical biology. And so the getting the invariants to be a rational function, to have all their powers, I mean, to be monomials with powers which are all integers, is quite easy. But if you restrict to that, like these invariants which were introduced in Murray, if you use these invariants, well, when you rewrite things, you will need to introduce square roots or fractional powers. So in many of these models, the quantities are positive, and this is not always a problem, but sometimes you need to decide on what is the sign, and introducing fractional power can be a complication. So in this example, our algorithms will kind of bring out the other invariant. So we are taking new, different invariants. And with these invariants, our system, which are kind of have all their powers to be integers, then when we reduce the system, we are not introducing any fractional powers. So that will be the advantage, the main advantage, the essential advantage, I should say, of the algorithms and the method we propose. So this is kind of the end of the introduction and showing you what is the purpose of this talk. If there were some questions at this stage, I'd be happy to entertain them. I'll just check in the Q&A and okay, so just I'm going to wait. Maybe I'll have a sip of coffee while you think of questions you want to ask.
The first question, Evelyn, is what Maple package do you use for this job? You're probably going to answer that anyway, but.
Yes, so as we will see, the algorithms are pretty simple. The only thing you need is the Hermite normal form. And this has been implemented forever in Maple. So.
And someone would like to look at slide 5 again, if that's okay.
Sure. Okay. 5, that's what I have as slide 5.
Okay. And I hope that answers the question that you had, Robert. And then another question says, is there always a way to find scaling factors to create dimensionless parameters? And this one might lead you to continue with your talk.
Yes, obviously there is, yes. Yes, so we will find them.
Okay.
All right. Algorithmically, I should say, we will find them algorithmically. That's the, we will always find them algorithmically. So it's not case dependent. All right, so I'm going to be, I might run a little late in my talk, but I'd like to still take time to kind of see what's happening with 2 dimensions, where we can kind of know exactly what are the computations to be done. So the first question we have, how do we find scaling symmetry? So this is, let's just look at this differential equation in 2 variables, x and y. And so scaling symmetry is something that will give a transformation of this type and what we want. So when we do a transformation of this type, we will obtain the same monomials in x, y, and derivative of x of y. And but in front of it, we will have some value, some powers of lambda. And so to obtain a certain homogeneous, to have a scaling symmetry, you need these 2 powers, this one and this one, to be the same, so that you can factor out this value outside of the equation. So what does it mean? I mean, we just put that these 2 things are equal, and that's a linear equation in A and B. And for the rest of this talk, we will see that we are going to write it as a row vector, AB, which are our unknowns, and multiplied here by a column vector that we want to be 0. So it's pretty, I mean, it's we're pretty sure that A and B, such A and B exist. But let's say that we have a third term here. This third term also adds, what does it do? It actually adds a new column. So now we are looking at a possible, so this term here adds a new column, this column given here. So now we are looking for a left kernel of a matrix, of a 2 by 2 by matrix. And there would be more columns if we had more terms. Okay. So if by any chance there is such a AB, we would like to choose A and B to be, since all these things are integers, I mean, you can always find AB that is also consists of integers. And it makes sense to choose A and B that are kind of the smallest in some sense, in the sense that any of a solution, which are made of integers, shall be a multiple of A and B. So I want to illustrate what these scalings are. So for instance, if you have a scaling that is given by this matrix, like we determined earlier, to be -2, 3, so that means that behind the scene, there is a group action that is given by a parameter lambda, and it acts on a vector xy by scaling x by lambda to the power -2 and y to the power by lambda to the power 3. So you see that this shape is transformed, the purple shape is transforming the pink shape under such a transformation for a given lambda. Another way of thinking of this transformation, of this group action, is to look at the orbits. So our scaling is represented by this matrix. And this, so I'm looking at all the points. So on this, so the curves of the same, the curves in one color are all the element x, y that can be attained from another point in this curve by a group element. So here we have, if A is 1, 1, we have nicely some straight lines, and we have curves of higher degree if we take some other entries to our matrix A. So I will explain later what is this black line that I have drawn here. So now let's look at what are the invariants of this scaling, because in the end, it's what we want. So we want first to compute the scaling symmetry, and next, the invariants of such a thing. So an invariant is going to be a monomial, x to the power c, y to the power d, such that when you substitute x by lambda a x and y by lambda b y, well, you obtain exactly the same thing. You obtain again x c y d. And so just as before, that means that C and D are in the right kernel of the matrix AB. So for instance, we could choose to be C to be minus B and D to be A. But if, for instance, A and B have a common divisor, that would be a bit, we wouldn't get the minimal general invariant. So what we're oops. So let's say that H is the GCD of A and B. And then we can take C to be the quotient of A by this GCD, and same thing for D, the quotient of B by this GCD. And now we obtain kind of what we can show to be the generating invariant, in the sense that any other invariant can be written as a polynomial of this quantity. So let me show you how this generalized to a higher dimension. Let me first say, write down the Bezout identity, which writes the GCD as a linear combination of A and B with coefficient alpha beta. And so with all the quantities we have now on this slide, we can write the equation for the Hermite normal form. So the Hermite normal form of the scaling matrix here, on the left, multiply, with some row operation that are described by this Bezout identity or this generating invariant, is equal to something in a very specific form, that is first the GCD and then 0. So this is a special case of this is the Hermite form of the matrix AB, of a scaling matrix. And this is obtained by multiplying on the right this scaling matrix with this multiplier, so-called multiplier, Hermite multiplier. And this is with this Hermite normal form, and more specifically with the Hermite multiplier, that we will be able to compute generating invariants and have rewrite rules and also lift formula. So as an example here, coming back to the scaling that we've seen before, the Hermite multiplier for this case here was here. And so you see that the right column gives you the invariant. So that the invariant is x to the minus 1 and y. And same thing here, then the invariant is x, y, and here x minus 3y. And so now the black lines that I have drawn here, you should observe that they have only a single point of intersection with each orbit. So when those are straight line, it's no big deal. But when the curves, when the orbits have a higher degree, then the fact that it has only one point of intersection is rare. It's a very special case. So for instance, here in this case, if we had taken vertical line, we can immediately see that every orbit would have at least 2 intersection points. So this is taking this line is very distinctive in that it has only 1 point of intersection with each orbit. So I'm not going to emphasize this rule, but this was actually by how we kind of got to understand those results about scalings, because this definition of section is how you get in general invariants and replacement invariants that generalize the very explicit construction that I'm going to give here. And it generalizes them for group actions other than the scalings, but in a less explicit form. So I want to go through what is a Hermite normal form, since it's going to be our main object and what unrolls everything of our construction. So a Hermite normal form is, well, something canonical, and this canonicity, so I'm going to speak about the column Hermite normal form. Understandingly, there is also a row Hermite form that you just need to kind of translate row into columns. So this Hermite form is going to have some zeros as the last columns, and then on the right and on the left, you will have a triangular shape where the diagonal terms are bigger than all the terms that come afterwards. And all the entries are non-negative. So the Hermite form is not so important, but what is, I mean, in this talk at least, and what is important is how to get from any matrix, in particular a scaling matrix, how to get to a Hermite form. And this is done with column operations, and these column operations are described by a matrix, a unimodular matrix, so that is a matrix with integer entries that is invertible over the integers. So there is this matrix, such that when we multiply on the right A by V, we obtain the Hermite form. So let me split this matrix V just as the Hermite form is split into something triangular and some zero columns. You see then that Vn is part of the kernel of A, and actually it is a way stronger result that the columns of Vn, the columns of the right part of V, they form a Z basis of the integers element in the kernel of A, meaning that not only it spans the kernel of A, but any other integer element of the kernel can be written as a linear combination with coefficient in Z of the elements of the columns of Vn. Okay, so this is what is going to give us the invariance, as we will see. I should add that the contrary to the Hermite form, which is unique, the multiplier is not unique. I mean, as you can see, I mean, you would obtain also the same Hermite form if you combined the columns of Vn, or if you combine the columns of Vi with some columns of Vn. So it will. So we introduced a normal form for the multiplier. And this normal form, we obtain this normal form by putting Vn into a Hermite form and by having Vi reduced with respect to Vn. So I'm not going through too much the details, but this is how we're going to use this unique multiplier to see when we can reduce the parameters in the simplest way. So for the complexity savvies, there is we have here is the complexity of the of how to compute this normal multiplier. And it's reasonably polynomial. So I'm going to move to the next section. So as I said, I mean, the Hermite form is the only thing we will need to make our algorithm work. And so it's all available in Maple. So so now we are shifting to how we use this ingredient to compute the invariants, the rewriting. And actually, we are not going to speak of the section, sorry. So again, I kind of introduced it in the introduction. We are going to use some matricial notation for the exponents. So if you have a row vector of indeterminates or variables and a column vector of integers, then the monomial lambda to the power a is this monomial. This is a standard notation. And what we are doing is that we are extending this notation to matrices. So now lambda raised to a power a is again a row vector, which the entry of which are the monomials given by each column of the matrix A. So everything will make very much, it will really simplify, I mean, makes it really works nicely. In particular, if you introduce the component product that I will denote with a star. So if you have two row vectors of non-zero entries or indeterminates, then you can make the product by doing this component-wise product. And this component-wise product works nicely with taking a matrix exponent. It just works like you would think. And so that makes for very compact proofs. So a scaling, as we've seen, is given now by a matrix that has n entries, and is the number of this, I mean, is the dimension of the space where we operate, and as it has n columns, and our rows are being the dimension of a group or the number of parameters in your scaling. And we can write the action of a set of parameters, I mean, of a parameter lambda on an element z of Rn by, thanks to this component-wise product, by having taken raised lambda to the power a. So this is the example we've already seen before. It's only one variable, and I hope you get the idea for the bigger variables. So let's look at the invariants. I mean, it's not going to be so surprising, but if we have a Laurent monomial, which is given by a vector v of integer, then this monomial is going to be invariant if when we replace, when we rescale its components, so when we do this operation, we end up with lambda to the power, to z to the power v, with the same monomial. And so with the operation we've seen, we see that this amounts to this equation, that lambda to the power av should be actually 1. And that means that v should be in the kernel of A. So this is first ingredient. How to decide if a Laurent monomial is invariant is to check that its exponents are in the co-kernel of the scaling. Then you can also kind of show, and it's not that complicated, but if you have a rational invariant, that's a polynomial, so it's the quotient of two polynomials, then it is invariant if and only if it can be written as by dividing the numerator and the denominator by one of the monomials in the support. It is can be written as the quotient of two sums of Laurent monomials which are invariants, so whose exponents are in the kernel of A. So I kind of left the proof, but you can just look for it, at it. So, okay, so the invariants are given by the columns of integers in the kernel of A. But we have a better, so using the Hermite form of A, we will find the matrix V that we decompose on one hand by this a basis for the kernel of A, and something else that is not going to come in this talk so much. And the result is that this Vn, because it generates over Z the kernel of A, we can show that the monomials that are defined with these columns, so G is here, is a set of n minus r, r being the rank of A, of n minus r monomials, and these monomials are given in this matricial form compactly. And these monomials form a minimal generating set of rational invariants. And to prove that, we actually obtain, the proof of that is actually a stronger result, namely, so not only, so if we have another rational invariance of our scaling, so we should be able to rewrite it in terms as a rational function of our generating invariant. And this rewriting is actually explicit. This rewriting is explicit. It is just a matter of replacing Z, which is Z1, Z2, up to Zn, by G, the vector G, raised to a matricial powers. And this matricial power is nothing else than the lower part of the inverse of our Hermite multiplier V. So when we compute V, since it's obtained with column operation, it is no cost to compute its inverse at the same time. So that's why I say it's a side product. We can compute the inverse at the same time. And with this inverse, we have the rewrite rules. So I'm going to, because this formula might be a bit new with all these matricial powers, I'm going to show on an example what it all means. So here we have a matrix A that is, so it acts on a 6-dimensional space. And we have a 2-dimensional scaling symmetry, so 2 parameters. Did I say 6-dimensional? 5-dimensional, actually. So the first thing is that we compute the Hermite normal form. And again, what is interesting here is to obtain the Hermite multiplier that is here. Oops, that is V here. And we have put V in this normal form that I have shortly described. Its inverse is obtained here. So this matrix V is cut into the column that corresponds to the kernel of A. And here this is split in the last row that will give you thus the rewrite rules. So the generating invariants are given as monomials, this monomial being decided by this right column of V. And the rewrite rules, that is how we kind of, by what we substitute Z1 up to Z5 in an invariant to write it in terms of G. Well, it's given by this set of monomials that is given by the bottom rows of W, and more explicitly here, those are these monomials. So for instance, here we could check that this is an invariant, and with this rewrite rule, we know that we can write it as just G2 times G3 minus G1 minus 1, where G1, G2, G3 were obtained here. Oops, okay, I think this is a mistake. Okay, sorry, I left some slide in. So, okay, so we have seen how to compute invariance and how to compute rewrite rule. Let me say how it applies to the parameter reduction, which is the whole subject of the talk. So the system we want to deal with, they bear on some parameters, C1 to Cp, and some variable, Z1 to Zq. And we shouldn't forget time, which will be one additional variable. So our dynamical system can be written dz of a dt is equal to a function, to a vector of that depends on C, on the parameters, the time, and the variable Z. So I've spelled it out here. So a scaling that is given by a matrix is a symmetry of this system if you have each equation has some is homogeneous. And that amounts to say that if you take instead of F1, if you look at if you form for each I, T times Zi minus 1 multiplied by Fi, this quantity should be an invariant. And then that's to say if when A is a scaling symmetry. So so now to say that such a polynomial, such a rational function, is an invariant, we first normalize, that is, we take something, a monomial in the support, and we take its exponent and we take it away from all the terms in the numerator and the denominator. So now for F to be an invariant, you need that all these exponents are in the kernel of A. So we can make this matrix of all these exponents. And what we want, and we do that for each of the components F. And what we want is the left kernel of this matrix. And so this we can obtain a different way, but as we've seen, we can use the row Hermite form and take we take the multiplier, and on the multiplier, we can read what this scaling should be, A. So we can read from the multiplier the scaling symmetry of our system. Okay, so we know what is the scaling of our system. So what we need next are the invariants. Okay, the invariants are read from the column Hermite form of A. This column Hermite form consists of, we split in two parts. So the blue part, Vn, is what gives you the invariant. And what is practical for us here is to have the matrix. We would like this matrix to have some zeros here at the bottom left. Because then we know that we can kind of, we will reduce by the size of this matrix the number of parameters, and we are not mixing parameters with variables. And it's actually, if we want things like that, we want a Hermite multiplier with some zeros like that. How do we detect that such a multiplier exists? Well, this is where comes our normal multipliers. If such a Hermite multiplier exists, that means that the normal multiplier will be of this shape. It will have a matrix, an identity matrix in the right bottom corner, and those are all zeros. And so the inverse will also have the identity matrix in this corner. So I have divided here again my matrix further. I have the columns that corresponds to the variables. I have one column that corresponds to time. And here I have the columns that still corresponds to parameters, and these all correspond to parameters. So that means the following, that we can take as new parameters the monomials which are obtained from this matrix. For time, we can rescale time with a bunch of former parameters that are given by this matrix, by this column, I should say. And finally, the variables, the new variables, are simply obtained by multiplying by each of the former variable by the monomials which are given in this matrix. We actually obtain a very explicit form for the reduced system. So this formula is actually difficult to digest, maybe, but it's very easy to program. So it's only a few lines of Maple to program such a thing. And the next bonus is that so we have the new variables. We have how the reduced system as a formula. And furthermore, the inverse matrix gives us how to lift a solution. If we have a solution of the reduced system, we will obtain a solution of the original system by this formula. So again, I'm not asking you to read, I'm not going to try to make you understand all those formula. I'm just going to show you on some example how they come out. So this is the another model that you can take in the mathematical biology book, the logistic growth. So the variable is n, the parameter is r, the parameters are r and k. First thing, we determine the scaling symmetry. Well, it's given by this matrix. Hermite multiplier gives us some of the invariants of the new variables. And the inverse matrix of the multiplier gives us the rewrite rules. So the rewrite rules are kind of simple. You see that some parameters go to 1. All the parameters actually go to 1. So here you can eliminate all the parameters. And you obtain the new, and then you t and n directly go to these dimensionless variables, n and t. So the lift formula, so if we have here, this is a very simple equation. So we can write a solution by a general solution by introducing this integration constant. And from this solution of the reduced system, applying the formula that I kind of popped in the previous slide, I can obtain a formula for the original system by this formula here. So we can do the same with more system. I'm happy to show them to you. So here, this is the reaction kinetics, compute the scaling symmetry with a Hermite form, row Hermite form, and then apply a column Hermite form, get the normal Hermite multiplier when it's inverse, determine the new variables, the invariants from V, and then the rewrite rules from W, deduce the reduced system, and then deduce the lift formula from W again. And I had a bonus track to say that this parameter reduction scheme that might appear where I kind of said that I wanted my normal multiplier to be of the specific form. We actually don't, I mean, we can always do scale, as soon as we have scaling symmetry, we can do a reduction independently on how the normal multiplier looks like. But this is something that I could go through if there were some interest, but I'm going to leave it at that for the moment. It's a kind of interesting robot. Another time. And with that, I'd like to thank you for your interest. I wanted maybe to finish by, now let me just still say that we tried this approach on as many models that we could find in the literature back when we wrote the paper. And I would say that 95% of the models that we looked at, we could apply our automatic reduction technique to them and obtain the maximal parameter reduction.
Very nice. Very nice. Well, thank you very much, Evelyn, for this wonderful talk. We have a bunch of questions for you, but first, you'll have to take my applause for everybody's applause, but there we go. It was a beautiful talk. We have a quick question from Stephen, who has to run at 3 minutes or 2 minutes. He says, have you run into situations where you have two different types of things that use the same units, where you have to separate them into distinct groups and categories?
So, what?
Well, it's a long question. It's in the chat. I think we'll let you talk to Stephen about that one later. We have a shorter question. People want to have your slides, of course, but the shorter question that came up was this idea of the parameters going to 1. Of course, that's the key part of dimensional reduction, but it's often the part that people find hardest to understand. Can you say a couple more words about how the reduction actually happens? For example, on slide 28, you have parameters R and K going to 1. I know it's the point.
On slide 28.
Yes, it was just one of the examples. You also did it very, very early on when you divided. So you go R going to 1 and K going to 1, which is the point of dimensional reduction. You're removing some parameters.
Yes. And so the question is, how does this happen?
Yes.
So if I want to explain, the explanation that comes to mind immediately is a bit to what I just hinted at, is that if you have a system that is invariant under group action, so here the scaling, this reduction, what it does is that it, instead of each orbit, it takes 1 point. It picks 1 point per orbit. And this 1 point is going to be on the section to the orbits. So it's like reducing to this section. So this section I just showed as the straight line that we saw some section in the, let me go back, yes, here. So here you have the full picture. The full picture has symmetry. So that means, so you want the reduction, it's kind of taking all this orbit of solution, all this orbit that is given by the points on the same line of the same color. And all this orbit, I'm just going to collapse it into 1 point, which is the intersection of this section with the orbit. So somehow, here, because this thing is, this section is x equal 1, the reduction is going to bring x to 1. And then y is going to be taken, then it's y that is going to change. You need to push y along this orbit. All right, so it's kind of a geometric explanation of why you get things to 1. It's not always like that. It's sometimes the reduction, here in this example, all the sections are straight lines, but they could actually be curved lines. And actually, yeah.
That's a very good way to think about it. I think that will help. I don't know why that particular point is difficult to get across, but that's exactly the sticking point in understanding dimensional reduction as taught to engineers with all the fractional powers. So, and there is that moment of getting it over. Okay, we have 2 more technical questions. First, the rewrite rules are not unique. The answers are the answers you're getting with your approach satisfactory in practice? So that's a practical question. And then the second part of that question is, can you do more general things rather than just multiplicative scalings? Can you do other symmetries with this approach?
Yes, so the first part of the question is the rewrite rules are not unique. So what is not unique is the set of generating invariants you use. So once you fix the generating invariants, I mean, the rewrite rules, I would think, are determinants. Just, yeah, I would think so. Maybe not. Okay, but they go hand in hand. The second thing is, can we do it more generally? Yes. And actually, this is somehow the ideas from this work are coming from a more general theory, the theory of moving frames, and where this reduction can be done for more general groups actions. So what is special here is that everything becomes so explicit and can be done with linear algebra. So the more general theory of moving frames and the algebraic version of them that I worked on, but I have some very nice results with Irina Kogan on this topic. If you want to compute the invariance, and more specifically the differential invariance, you will typically have to compute a Grobner basis, so that's tougher. There is this very interesting question. I mean, first of all, is there a rational section? So a section with only one point of intersection with each orbit. And if there's such a rational section exists, how do we determine it? So here we have this rational section all the time. It's given by the left column of the V matrix. And so this also kind of brings some complexity. I mean, so these points are not answered by the moving frame technology, but we can compute the invariant. We can say how to rewrite things. And also we can also do the lift technique, but this becomes way more ambitious and less explicit. But it does exist. The more general theory exists, and I actually had put this paper with Irina to kind of bring some directions to it. This is also a more recent paper that also looks at the invariance of the orthogonal group by refining the techniques of the moving frame as well.
Excellent.
Thanks for this question. It's really nice. Thank you.
Thank you very much, Evelyn. And now I'm afraid that we are over time, and I have to call time, but say thank you very much again for a beautiful talk. And I ask anybody to direct further questions, and we can to us, and we'll pass them on to Dr. Hubert. And I am required to say one more thing, which is to announce the winners of the art gallery. I put them in the chat. Paul DeMarco has won People's Choice, and the overall judge's choice was the Hadamard 160 in Cool Tones by Bridget Lee and Curtis Bright. And the judges gave a special recognition for a student contribution, Rotating Hypercube by Avik Dongo. So with that, we're about to be cut off by the service, but thanks very much to everybody who came, and thank you again to Evelyn. Thank you for letting me trespass a little bit on your time with this art gallery announcement. Okay, thank you everyone for coming.